Hello everyone, my name is Karan Chahal and I've been working on a convolutional neural network. This convolutional neural network is basically trained on the CIFAR10 dataset, and what it does is that it basically takes the image and classifies that image into one of 10 classes. So the convolutional neural network works by first importing all the different libraries that we are using in the program. So import torch, import torch.nn, which is the neural network library with PyTorch. And if I haven't already mentioned it, I created this convolutional neural network using PyTorch, which is a very good framework for creating neural networks of any kind, and it really helps you visualize how a neural network actually works in practice. And after importing all the libraries, the next step that I took was to first define what device are all these computations that the neural network is going to be performed on. And I told the neural network that if the GPU is available to conduct the computations on there, which is what CUDA means, otherwise just use the CPU. In my case, I did not have a GPU available, so all computations were conducted on the CPU. And after this, we have the hyperparameters, like the number of epochs, the batch size, and the learning rate. So after defining the hyperparameters, the device, and importing all the libraries, we go into the transformation. So for the trained dataset, which is the CIFAR10 dataset, I want to perform some transformations. One of them is that I want to change all those images into tensors so that we can actually work with them. If they were images, we wouldn't be able to work with them because, first of all, PyTorch works with tensors and it can only use that, and it can't really handle the image format. In addition to this, that 2-tensor basically allows us to make all those images which have their different pixel values and convert them into a tensor, so you have only numerical data, because AI algorithms, not AI, or you could say deep learning algorithms, only work with numerical data, so that's very important. The next thing is to normalize it, and this basically means to find the z-score for each of those pixel values in each of the images. And normalization overall really helps the neural network in learning and recognizing patterns within the data set. And the next two transformations are basically, you could say, an example of data augmentation, where we're randomly horizontally flipping some of the images and randomly cropping some of the images. And this really gives the neural network some flexibility and doesn't really make it too, you could say, specific for the trained data set. What happens sometimes is that if you don't do these data augmentation techniques, you have a neural network that has a lot of accuracy on the trained data set, but when it comes to the real world, it can't really handle it because it hasn't really seen, an image flipped or something like that. So this aspect really gives it more flexibility, and it prevents overfitting of the neural network. Next is the transformations for the test dataset. For the test dataset, I just kept it the same. I didn't perform any random horizontal flips or random crops, and that's basically the only difference. We still conducted the .2 tensor and the normalization of that dataset. Then we import the datasets and we create the corresponding loaders, data loaders, and then we define an array, classes, so the plane, the car. So these are all the different, you could say, classes that we'll be classifying images into. And after we have all these classes and have made the data loaders, we are ready to actually make the convolutional neural network. This is where it actually gets fun. So the first aspect in PyTorch is to obviously define each of the layers. So you have a convolutional 1 layer, and then a convolutional 2 layer, and then a convolutional 3 layer. In this neural network, we had 2 pooling layers, but we only had to define 1 pooling layer because they were all the same. And then we also defined some linear layers, which are basically the hidden layers of a neural network. And here we could see that for the linear layers, it's taking a 128 by 8 by 8, and it's outputting 200. So it basically has 200 nodes, and this one has 10 nodes in the last linear layer, or you could say last hidden layer. And then for the convolutional layers, they all have kernel filters of 3, and you could see that they have different arrangements of inputs and outputs. One thing to recognize here is that why do we have an input of 128 by 8 by 8? The reason for that is because after we conduct all the convolutional layers and the pooling layers, we can actually calculate what the image size would be. So conceptually, it would be 128 images of 8 by 8. Now, the thing with neural network training is that we have to flatten that into a single, you could say, a single like data input or input layer. So it has to be not multi-dimensional. It can be like 8 by 8 and then 120 of those. You can't really feed that into a network. You have to flatten all of them, and that's what that multiplication between all of them does. It basically makes them all flat. So it's basically just a long list of the pixels of the images. And then we define the forward function for the convolutional neural network. And the forward function is basically, so for the first convolutional layer, we perform the convolution, and then we use the ReLU activation function on that after performing that convolution, and then we perform the second convolutional layer, and then we perform the activation function, and then after that we have a pooling layer which conducts pooling, and then in this similar manner we go through the network, and in the end we return at the linear last layer, or you could say the last hidden layer. And basically this kind of acts as the output layer, the self.nn.linear 210, and we don't really perform any activation function here because the activation function would be softmax since it's a multi-class image classification. But since we are performing cross entropy in PyTorch, we don't really need to add that activation function because it already performs it automatically with the cross entropy. Now, the next is that we define our model. So this is actually creating the model. So we had the classes, and it basically creates the model with this line. And then we have the criterion, which is basically like the loss function of the neural network, and that's cross entropy, since this is a multi-classification problem. And then we have the optimizer, is using stochastic gradient descent. And after this, we go into the training loop. So we're basically going in for each epoch, we're taking those images and labels, and it's split up into batch training. So it's taking at 10 images and labels at each time because our batch size is 10, and then it's going through the train loader, and then it's going through all the batches in one epoch, and then it goes to the next epoch and the next epoch, because epoch is basically when we have gone with all the data through the network and we have conducted all those iterations with all the data. So that's what an epoch is, whereas batch is just you have 10 images, 10 labels, specific for us, obviously, and then you're training with that. And then with the different batches, so right here, we're basically defining what we're doing with each of the batches. We're basically taking the images, putting it on the device, labels, putting it on the device. Device is still CPU because it's not available. And then we have outputs. So the outputs are basically the model images. So that basically means like the predictions of the model. But the thing with predictions with the model is that it's really in terms of different probabilities. So it's not exactly the prediction, it's kind of like the outputs of what the model gives you. And then after that, you can get the predictions in this way by doing torch.max. But after getting those outputs, we then use those outputs with the labels, and we do the loss function, and this is where the criterion, basically like the loss function, comes in. After figuring out that loss, we do the gradient of the loss to the weights, and then we do the optimizer.step, which basically changes the weights each time. And then for each epoch, we type in the epoch, the step, and also the loss and how it's decreasing over time. And then after it's been finished training, we print the finished training. And then after this, we basically have a accuracy calculation. And how this in fundamental works is that we're basically taking each of those images and labels in the test loader now. It's not the train data set. We're taking it from the test loader, you could say test data set, and we're basically checking, we're basically making it predict in real time and then comparing that to the labels, and in that way we have two different arrays with, oh, this is how the predictions went out for each of the classes, this is how it should have went out, and then in that way we figure out, oh, this is how much the accuracy of the network is, and then we also print out the accuracy for each of the classes for the network. And then we do the same thing with the test data set. The accuracy we are using is for the test data set, but we also did it with the train data set, and the reason for that is to just make sure that we're not overfitting our model on the train data set to just see like, oh, what's the accuracy comparison between the two. So if we did the accuracy on train data set and we found, oh, it's 99%, whereas for the test data set it's 50%, we could figure out that, oh, the model is not actually ready for the real world and it's overfitting. Now, keeping all this in mind, we then move on and we basically just do a little bit of an example showing the 10 images, their corresponding labels, and what the model predicted. So let's see the output. So in terms of the output, you could see that as we train the model, the loss actually goes down over time. So if you had like 100 epochs, you would probably have a higher accuracy. And then here is the accuracy statistics for the test data set, and then this is for the train data set. And what we find is that for the train data set, we have a higher accuracy. And if this was even higher, it would kind of indicate that the model is overfitting. And then here is like that example code that was there. This is basically what it does. It gives you those 10 images and it says, oh, these are labels for the 10 images. And this is what the model predicted for image 1, image 2, image 3, and as follows. And we could see that it's correct for the image 1. It's also correct for image 2, which is a plane. It's correct for image 3. Image 4, I don't really know myself what that is because, oh yeah, that is a dog. So yeah, it basically predicts depending on the image it's given, and it classifies it into 10 different classes. Overall, after really learning about convolutional neural networks and actually applying them, I really see how they can be applied in the real world and how strong these deep learning models are. And I think that in the future, these deep learning models can really be used to solve real world problems. Specifically, I'm thinking in the medical field, like for diagnosis, you could really use image classification in order to see, oh, which person has cancer and which person does not. And we could see AI really making its way into those types of fields. Overall, I hope you guys have a great day. And yeah, that was my project.